In this presentation, we'll examine common valve and regulator failure modes. The most common failure mode is leak across the seat caused by contamination. An outboard leak, that is, a leak from the internal cavity to atmosphere, is very rare. If a valve or regulator works properly for a period of time and then fails, most likely something caused it to fail. For example, it may be the wrong regulator or valve for the application, improper use, or contamination. The across-the-seat leak is usually caused by particles lodging between the seat and the poppet, or the seat and diaphragm. These particles prevent the valve or regulator from fully sealing and allow gas to leak across the seat. These failures are generally caused by foreign matter, contaminants from the cylinder, gas separating or decomposing, and/or improper purge technique, or a combination of these causes. For example, a Diborane cylinder, if not stored at the proper temperature, could create particles from partial decomposition. If there is contamination in the gas stream, it tends to precipitate and deposit on the low pressure side of the source regulator's poppet due to pressure and temperature drop at the seat and poppet. In this image, we have light etching of the low pressure surface of the poppet causing hazing. The hazing starts where the pressure drop occurs and stops where the poppet meets the seat. This image shows dark particulate contamination on the low pressure side of a regulator. Often the chemical composition of the particulate matter is difficult to identify. Even with extensive lab analysis, the identity of the contaminants are generally inconclusive. This image shows foreign fibers attached to the sealing surface of a seat. Foreign matter on the sealing surface will often cause the valve to leak across the seat. This image shows unknown contamination on the sealing surface of a regulator. Static leak testing failure after piping installation is often caused by stainless chips or shavings from tube-facing operations. In this image, a valve leaked across the seat due to the metal shavings depositing on the seat. Corrosion can also cause regulator and valve failures. Corrosion is usually caused by moisture reacting with the metal alloys used in the valve or regulator. Moisture can enter the system due to improper purging, moisture in the gas cylinder, and leaking fittings. This image shows a face seal fitting with corrosion. As previously stated, an outboard leak is very rare. This is leakage from the inside of the valve or regulator to atmosphere. On the rare occurrence of an outboard leak, it most often leaks due to a crack in the diaphragm. An outboard leak can be caused by corrosion and/or induced by excessive cycle purging, overpressurization, or excessive flow, sometimes resulting in stress fracture of the diaphragm due to metal fatigue. In these images, a tied-diaphragm regulator is overpressured, causing the diaphragm weld to fail and an outboard leak. Here's an example of a new tied diaphragm with convolutions on the left and an overpressured diaphragm on the right. Convolutions are the concentric curves that allow increased movement of the diaphragm. The thin metal diaphragm yielded due to overpressurization. On the right, the scalloped edge outside of the area where the diaphragm is clamped to the body is indicative of a diaphragm being overpressured. This may or may not cause an outboard leak. In this image, there is corrosion on the surface of the diaphragm normally caused by moisture reacting with a corrosive gas to form more chemically aggressive aqueous corrosives. Over time, excessive moisture in contact with the diaphragm can lead to through the diaphragm leak failures. In this image, the diaphragm on this free poppet regulator cracked due to excessive cycling. The cause of failure is stress fracture due to metal fatigue. The location of the stress fracture is often at the point of highest stress near the outer convolutions. Other causes of failure are operator errors. This includes selecting the wrong regulator or valve for the application. For example, materials of construction are not compatible, or the regulator is sized improperly for the flow or pressure. A failure mode that is particular to tied diaphragm regulators is pressure lockup. If an operator closes a tied diaphragm regulator with excessive trapped static pressure under the diaphragm will pull the poppet into the seat, damaging the seat and poppet. The majority of regulator and valve failures are not due to manufacturing defects. Failures are generally caused by contamination, moisture, gas reaction, and improper use or wrong selection. It is unusual for a failure after startup to be the fault of the manufacturing. Defects are often found during startup and testing. If a regulator or valve operates normally during startup and functions for a period of time prior to failure, some external cause is likely. There are some common regulator occurrences that may cause concern, but are normal. Some regulators will have a noise coming from the bonnet vent hole, usually higher flow regulators. The cause is gas flowing through the regulator, or it can be caused by an external source of vibration. In either case, the diaphragm acts as a loudspeaker. A soft sound is usually not a problem. A squeal or humming noise is a sign of the regulator being unstable and can lead to failure. Regulator sweating is when beads of moisture form on the regulator surface and are not a problem. The cause is the gas expansion cooling effect, condensing moisture on the regulator surface from humidity in the air. The countermeasure is heating, clean dry air external purge, or to ignore. It is important to not let water drip on electrical devices. Our recommendation is to ignore regulator sweating. However, white frost may be a problem and must be investigated. See product note number 407 for more details. As we just examined cooling effects due to gas transitioning to a lower pressure, there are also the opposite heating effects due to gas compression or increasing pressure. This is called adiabatic compression. When a gas compresses or pressurizes quickly enough to avoid heat transfer, it is considered adiabatic. The increase in temperature can be significant and cause ignition in the presence of an oxidizer and fuel. There are accidents every year with residual oil present in the inlet connection when an O2 cylinder is opened. This is the purpose of the cleaned for O2 service requirements and components that are marked use no oil. All APTEC products are cleaned for oxygen service. Ultra-high purity requirements are more stringent than guidelines for oxygen cleaning. While the classic adiabatic compression failure is oxygen and residual oils, even inert gases and polymers can experience adiabatic compression failures. In this test, a valve is partially opened and pressurized quickly one time with 2000 psi of nitrogen. The PCTFE valve seat melted due to the heat from compression and the small flow of gas across the seat. In another lab test, a valve is closed with a small wire across the seat to purposefully cause an across-the-seat leak. The seat melted due to adiabatic compression heat and the small flow of gas due to the seat leak. Choosing the right materials for your application will ensure a long service life of the valve or regulator. The typical metals used are 316L stainless steel and high-performance alloys such as Hastelloy C-22 and Elgiloy. Elgiloy is typically used for valve diaphragms. Hastelloy C-22 increases corrosion resistance but does not eliminate it. It is commonly used for regulator diaphragms and other internal parts for highly corrosive applications. The valve or regulator body material is often 316L stainless, as high-performance alloys are not needed. Seat and seal material options are polymers such as PCTFE, PTFE, PFA, Polyimide, FKM, and FFKM. The most common seat material is PCTFE. There are two types of 316L stainless steel used by APTEC: single melt and VAR secondary remelt. VAR secondary remelt means vacuum arc remelt. Single melt is used on the AZ series products, and VAR secondary remelt is used on the AP series of products. Single melt material is less expensive and can have clusters of inclusions such as sulfides, which form stringers in line with the axis of the bar. Thin walls that are perpendicular to the axis of the bar have a risk of creating a leak path through a stringer due to corrosion. The stainless VAR secondary remelt material used in the AP series products has much lower levels of inclusions, making it a better choice for corrosive applications due to the lower sulfur level. See product note number 414 for a more detailed look at using single remelt versus VAR in corrosive applications. When selecting seat material for valves and regulators, ensuring chemical compatibility is very important. PCTFE offers the best combination of broad chemical compatibility and mechanical strength compared to PFA or PTFE. PTFE is preferred for regulator flow cycling applications where the seat has potential for abrasion-related seat wear. Polyimide has limited chemical compatibility. It is not compatible with strong acids and bases, but has much higher operating temperatures than PCTFE, PFA, or PTFE. A polyimide seat in some chemicals, such as ammonia, will dissolve. Now let's review the key information regarding failure modes. The most common mode of failure is leak across the seat. Failures are generally caused by contamination, moisture, gas reaction, improper use, or wrong selection. If a regulator or valve starts up well and functions for a period of time prior to failure, some external cause is likely. Noise at the bonnet vent hole and regulator sweating are not likely a sign of faulty operation, but ice on a regulator surface must be investigated. Adiabatic compression generates heat due to rapid pressure increases and can lead to ignition and seat melting. Single melt 316L stainless steel in the AZ series has more inclusions than VAR 316L stainless steel in the AP series. Use caution when using single melt in corrosive gas service. PCTFE is the standard seat material, but other materials have advantages in some specific applications. For more information about APTech products, go to aptech-online.com, where you can download product notes number 407 and 414 to learn more about how to manage regulator cooling and applications for using single melt and vacuum arc remelt stainless steels.